Hello, everybody. I'm here to talk to you a little bit about uncertainty as kind of a part one of a series that will go into the calculation and propagation of uncertainty from various components of measurement. Here I have a list of 7 items that you should think of as a checklist for determining your final uncertainty values that you'll report for a certain research topic or experiment that you end up doing. And I'll walk through each of these steps one by one in order to give a few extra details about each of them. Starting with the first item, determine all relevant equations. Quick note about this is that it may involve multiple equations. For example, one is x is equal to some function of a, b, and c, where the a, b, and c are just some variables that have no meaning outside of this example. And x may also be equal to another equation of other variables, e, f, and g. Those variables might overlap with the previous equation, or they might be unique. And then there can be sub-levels of equations where variable a, for instance, may be another function of some extra variables. Now, quick note of caution is that just because you look up an equation and it seems to have the variable that you're trying to go for, it does not mean that it is the correct equation. A lot of equations will have a certain number of assumptions that are made to simplify the equation, or it may apply to a different scenario. So always when you're figuring out the equation, make sure the assumptions are valid for your setup. Now, item 2, determining all variable values. For this, there are kind of 3 possibilities in general. The first is you can measure the variable, so that might be something like temperature or volume or pressure, etc. You could also look up a reference of that value, such as the ideal gas constant or the thermal conductivity or viscosity of a certain material. The last item is to find an equation that relates other variables to that target variable, which I already mentioned before. Now, make sure when you're doing these calculations that you convert all of your values over to SI units, or if you happen to be using another form, make sure that they get converted to that. Before you do any calculations, it doesn't actually matter the order, you can always figure it out later, but it's usually safer to just do it right away, and therefore you don't get any mistakes where you actually didn't convert from inches water to pascals, and that destroys your equations and values down the line. So the third item is to determine the sources of uncertainty for each of the variables. And that kind of depends on how you got that variable value in the first place from step 2. So if you're measuring it, you have the possibility of systematic uncertainty always is present in your system. And that usually gets reported as a percentage FSO, which stands for full scale output. Sometimes this is abbreviated as FS instead, so be aware that those are usually interchangeable. Or a percentage of reading, or just a straight nominal value like 1.2 millivolts or something like that. And there are random uncertainties from your measurement, and this is just a statistical term where you have a t-value, which converts between the standard deviation to a 95% confidence interval in the engineering fields, multiplied by the standard deviation divided by the square root of the number of samples in your random measurement. And then the last item is resolution, which is sometimes put into the systematic category, sometimes in the random category. There's a lot of debate there. And that usually comes in 2 forms. One is where it's just half of the smallest increment in your measurement. So if you think about like a ruler, for instance, each of those tick marks would be that delta x. And then the resolution uncertainty is just half of that delta x. Now, if you're dealing with some digital interface, then you would use this equation over to the right here, which is just taking the maximum range of values being measured by your digital system and dividing it by the total number of combinations from the number of bits provided by your device. So 2 to the power of the number of bits, 2 because they typically operate on a binary system of 0 and 1s. Now, if you reference to the value, then you have to check to see if they state what the value is of the uncertainty, which sometimes does and sometimes doesn't, depending on how technical the source is. Sometimes the uncertainty is really negligible. Some values have been tested again and again and again to the point where you've got an extremely accurate system, but other times the value will actually be absent entirely, and so you can actually disregard the contribution of uncertainty in this form. And then the last piece, if you had it calculated, then you would just go on and do uncertainty propagation, which would bring you all the way down to part 6. For the fourth step, you want to check to see if any of these sources of uncertainty are negligible. And the reason why you would want to do that is mostly to simplify your calculations. This isn't necessary. If something is negligible and you include it, the only difference is that you put more effort into getting the same answer. Negligible just means that if you include it, it doesn't really change your final answer. In order to determine if it's negligible, you want to take that relative uncertainty, or in other words, the uncertainty divided by the value you got the uncertainty for, and make sure that that is less than about 1/10 of the relative uncertainty of whatever is contributing the most uncertainty. Then you will make the assumption that that uncertainty that you're comparing with is approximately 0. Now, as an example, I'm going to bring in relative uncertainties of 3%, 3%, and 30%. And if you run through that calculation using the RSS method, you get the result being 0.303, which when you do some rounding, it actually turns out to basically be 30% still. So it's unaffected when you consider significant figures. Now, a note of caution, if too many of these sources exist, then this approximation isn't as valid. So if I had 30 different measurements of 3% uncertainty and then one of 30%, then it will actually have an impact on your system. But if you only have a handful of them, then it's fine to ignore them. So the next part is to calculate the total uncertainty for each of those variables, each of the variables that you've considered non-negligible. And for this, we'll use the root sum square method that I mentioned in the last part. And so an example of this would be if you're combining all the systematic uncertainties together. Forms of systematic uncertainty might be like accuracy, hysteresis, linearity, etc. There can be many different forms. Usually accuracy is the one you focus on, but know that there can be more than that. Then combine your random sources, so the random of measurement and your resolution. And then combine the systematic and the random together using the root sum of squares. You can also use all of them being root sum squared together as a single entity, and that doesn't actually change it, because if you plug in b of x into the first equation with u of x in it, you're squaring, which undoes the square root, and then it just becomes a string of squares summed together. So these can be interchangeable. For step 6, you want to propagate the uncertainty towards whatever your target variable is. In order to do that, you want to use the general form, at least to start with, which always works, assuming that the uncertainty sources are independent of one another. If they are dependent on one another, you need a covariance, and it just gets a little more complicated. But we'll treat the system as purely independent sources of uncertainty for now. And so the equation looks like this in its general form, where the uncertainty of x is equal to the square root of the sum of squares, where each of those items is the partial derivative of your target variable with respect to one of its constituent variables, multiplied by the uncertainty of that constituent variable. And so to play that out, we see this can be equal to the square root of the partial derivative of x with respect to a multiplied by the uncertainty of a squared plus the other terms where I'm only swapping out the variable of interest. Now, there is a special form to this equation, which does not always work. And I want to emphasize that it does not always work. There are some valuable times in which you can use it, but it is not your go-to. If you ever question whether or not you can use the special form, just go with the general form, because, again, that works. And this form basically has generally the same outline, except instead we've got this x bar term pulled out, and that's just the average value of your target. And then it's, again, the square root of the sum of squares. But inside that parentheses is now n of I, which is the power of the constituent variable in an equation. So it'd be like a to the power of 2 or 3 or 3.6, any constant number, multiplied by the uncertainty of that constituent divided by the average constituent value. And so again, we see this playing out here. In a lot of cases, the n's will be like 1 or 2. If it's 1, they just drop out entirely, and then you're just left with the relative uncertainties, which is really nice because if you only know the relative uncertainty, not either of the values, then this can really make your calculations easier. Now again, this only works if it takes a special form, which I have shown here, where it's x is equal to a to the power of n of a times b to the power of n of b times c to the power of n of c, and so on, where the n values are constants and the letters are variables. This does not work if you have situations like this, where you involve trigonometric functions, or the square root of the sum of various variables combined together, or the natural log of a variable, or 2 to the power, or some number to the power of a variable. In these cases, you would actually have to use the full partial derivative. Now, quick note, the RSS method that I mentioned before is just a simplification of the general form. If we recognize that you are taking the partial derivative of a value with respect to itself, then that partial derivative term just becomes 1 multiplied by your uncertainty, which then causes that partial derivative to just drop out entirely. So we can see this play out in the previous RSS method equations that I showed. So now it just becomes the root sum of squares. Now the final step here is to take the uncertainty and the value that you calculated and report it in the proper format, which involves taking the average value plus or minus its uncertainty along with its units, and then you want to format it with the proper significant figures. So a quick note about why we do this: x bar and u of x are completely meaningless without each other. So if you said that it'll take you about 5 minutes to get somewhere, but you don't tell them that it's plus or minus 10 minutes, then it doesn't really mean much of anything. Whereas if you say that you'll be within 10 minutes of time that you won't tell, then they won't know what reference you're talking about. So make sure that these units are together and that they are including the units, whether it be seconds or minutes or hours, can drastically change the meaning. So some rules for rounding is that if you're using uncertainty and it starts with a 1, then you want to keep 2 significant figures. Otherwise, you want to use just 1 significant figure. And the reason for this is that the error in your estimate is larger when the uncertainty is smaller. So like the difference between 0.14 and 0.1 is much greater than the difference between 0.94 and 0.9. And so it's considered more acceptable when you get past 1 being the leading digit. Now, the average value should have the same number of digits past the decimal point as your uncertainty. And this goes both ways. So if your uncertainty is, say, 20, then your average value should be rounded to the nearest tens digit. So here is a table basically showing how this can play out. I'm not going to belabor the individual examples except for the last 2. You can pause it if you want to verify it for yourself. The last 2 items actually involve scientific notation. And so a note on scientific notation is that if you have a really large value, like 10 to the 3 or something like that, then you'll want to use scientific notation. It can also go the other way if you have a really small value, like 10 to the negative 7. But when you do scientific notation, pull out that 10 to the power as well as the units, and keep the rest of it within parentheses so that you can more quickly compare the value to its uncertainty. And make sure that whatever you do not combine scientific notation with a more general form of notation, like we see in this bottom example here with the miles here. Last note here is make sure you only round reported answers. Anything that you're using a calculation should carry with it as many digits as you're capable. And the reason why I say this is because you can get rounding error, and most people will keep track of that, especially if it stays with you after you round your significant figures. So be careful about that. Now I'm going to walk through an example where I impose each of these steps along the way, and I'm going to focus this example around the time constant. The time constant in this case will be for a steel sphere with a thermocouple attached to it, measuring the change in temperature with respect to time. And so the equation we get here is the mass times the heat capacity of the sphere, divided by the heat transfer coefficient, multiplied by the surface area of the sphere. You can rewrite this equation as a function of m, c, h, and a. And I will talk about each of these items in detail. Pay attention to the color key off to the right, where anything in blue requires a calculation in order to determine that value. Anything in green is something that you just look up the value from a reference source. Red indicates a value that you are specifically measuring in an experiment. And then purple is an assumption that you're making in order to proceed with your calculations. So the mass is just a function of volume and density, and volume can be given by the diameter of the sphere. The next item, C, is a referenced value, so I won't give this here because it's not unpacking towards another function. But then H is calculated, and that can be calculated from the Nusselt number, which is a function of H, the thermal conductivity of air, as well as the diameter of the sphere. But it has an approximation, which is a function of the Reynolds number, Prandtl number, and the ratio of the viscosity of air between ambient condition and close up to the surface. And then the last variable is just the surface area of the sphere, which can be calculated from the diameter of the sphere, which is referenced. Now, within the Nusselt number, we see the Reynolds number, given in blue, is something that we need to calculate. And the Reynolds number is calculated from the density of the air, the velocity of the air, the diameter of the sphere, and the viscosity of the air. And a further layer down, we see that the velocity is also calculated. And so that is a function of the diameter of the orifice and the flow rate, which we'll be measuring with a rotometer with a FSO, or full-scale output, of 600 standard cubic feet per hour and a resolution of 10 standard cubic feet per hour. Now that we've unpacked all the equations that we'll be using here, which I'm only writing in general form just to not get lost in those details, which isn't the point of the uncertainty itself, we want to actually determine the values of each of these variables along the way. Down here to the right, I have provided the referenced values, given assumptions, and then the measured value that you would get from an experiment for this example. And most of these are already in SI units, but there are a few items, such as the diameter of the sphere and orifice, as well as the flow rate, which are not given in SI units, so we want to convert those over. Now we can just plug the numbers into the equations that are relevant, and here we've got each of these plugged in. Notice that I added H is equal to 62 watts per meter squared Kelvin, and the reason why I did that is because, remember, the H comes from the Nusselt number, which I calculated out at 60, and then I resolved that for H and then calculated what that value is. So for step 3, we want to figure out the uncertainties. For M, C, and A, these values are all either referenced values or functions of only referenced values. And for the sake of this example, we'll assume that all referenced values did not report an uncertainty. And so we will count those uncertainties as 0. Now remember, referenced values can have an uncertainty, but in this case, we are neglecting that. Now for H, on the other hand, we have to unpack this one a little bit because there are some sources of uncertainty here. For instance, the Nusselt number, the approximation equation, the function of Reynolds number, Prandtl number, and the viscosity ratio actually includes a 30% uncertainty due to the poor assumptions made in the equation. It just doesn't replicate the experiment very well. Now, if we proceed along this line, again, a bunch of referenced values, which we assume no uncertainty for, but then eventually we get down to Q, which is a measured value. So the measured value can be broken up into three components of possible sources of uncertainty. So the rotometer is quoted to have an accuracy of 2% FSO, and the resolution is always half of one of those tick marks. And then the random uncertainty we're going to assume is 0 because you're waiting until the measurement is approximately steady state and the fluctuations are smaller than your resolution marks, and so you are not able to measure that random fluctuation. And so if we walk through the calculations here, we end up getting the accuracies about 12 standard cubic feet per hour, and the resolution being 10 standard cubic feet per hour results in an uncertainty of 5 standard cubic feet per hour. Step 4 involves comparing the relative uncertainties of each of these sources. We already have the relative uncertainty calculated for the Nusselt number, which is 30%. But then for the flow rate, we need to divide each of those uncertainties by the reading value, which is 600 standard cubic feet per hour. And so we get that the contributions are 2% and 0.8% respectively. The 30% value is clearly the largest one, and so that one dominates the calculations. And then when we compare the other two values to it, we can see it's much smaller, much less than 1/10 of that relative uncertainty, and so we're going to consider those negligible. Now we want to figure out what the total uncertainties are for each of these variables. The dominant one, we're just going to leave that at 30%. It's already in its total form since there is only a contribution from the assumption itself. But for the flow rate, since the two terms are considered negligible and the other one has been approximated at 0 already, we're going to actually say that the uncertainty for Q is assumed to be 0. So now we can move on to step 6, where we start bringing together all these uncertainties into one final form. Starting with what we know, we've got the time constant equation and its calculated value. We've also got a value for the mass and the uncertainty being 0. The referenced value of the heat capacity is given with the uncertainty assumed to be 0. H, we need to unpack a little bit, which has a Nusselt number given at 60 with an uncertainty of 30%. And the area we calculated with an uncertainty of 0. Now, the uncertainty propagation in its general form for H gives us this, where the equation for H takes the form of the Nusselt number multiplied by the thermal conductivity of air divided by the diameter of the sphere, which if you propagate this using the partial derivatives of, again, H being the leading part of your partial derivative with respect to each of its components, the Nusselt number, thermal conductivity, and the diameter of the sphere, multiplied by the uncertainty of those components, and then sum of squared together with a square root over all of it. Remember, the thermal conductivity of air and the diameter of the sphere are considered to have no uncertainty contribution, so those terms will drop out, leaving only the Nusselt number. Now, for the time constant, it has the same general form. Again, this as mc over ha, so taking the partial derivative of tau with respect to each of its constituent variables, with m, c, and a having no uncertainty assumed, leaving only h remaining. So we have one term here. Note that this could also be assumed as the absolute value. Do not simply remove the square root in the square because the square by definition makes it positive. You cannot get a negative value for uncertainty. Now you may notice that each of these equations given here follows that special form that I mentioned before, where we can say the Nusselt number, K air, M, and C are to the power of 1, while D sphere, H, and A are to the power of -1 if you took them all as products. And so imposing that special form, For h, we get that it's equal to h multiplied by the square root of the square of the relative uncertainty of the Nusselt number, which we know already is 30%. So the square and does the square root, and we get 30% of h, which I'm just going to leave as this 30%, which you'll see in just a moment why I did that. For the time constant, same exact idea. We pull time constant out, and then we've got a relative uncertainty of h, which we already know from up here is 30%. Plug that in, so now it's just 30% of tau. And so we get about 83 seconds. Now we have everything we need for step 7. Step 7 involves reporting the average value plus or minus its uncertainty. And so we already know what tau and the uncertainty of tau is. And so in order to report that value, we would say that tau is equal to 275 plus or minus 83 seconds. But once we consider significant figures, we get that tau is equal to 280 plus or minus 80 seconds. And so we have officially succeeded in doing our calculations of the time constant. And you can follow the same framework for pretty much any situation with a few assumptions that I made along the way. Thank you for watching. I hope this has been valuable for you. Stay tuned for part 2, where I'm going to talk about, now that we have the uncertainty, what do we do with it? I hope you have a wonderful day.